see my screen?
Can do.
Okay, great. All right. Well, welcome everyone, and thanks so much for coming. So this is the webinar on Earth structure, rheology, and geodynamics. My name is Maureen Long. I'm at Yale, and I'm going to be leading the webinar. And later on in the hour, we're going to have short talks from Jeff Freimuller from University of Alaska Fairbanks and Paul Bedrosian from the USGS. Let me just advance the slide here. Yes, so as I'm sure everyone is aware, this webinar is tied to this upcoming workshop on future seismic and geodetic facility needs in the geosciences, which is going to be held in Leesburg, Virginia next month. And in advance of this workshop, a series of webinars is being held, and really the purpose of these webinars is to engage members of the community who aren't going to be attending the workshop in person. And so as Andy mentioned, this is the fourth in a series of 4 webinars. So over the last week, there have been webinars on supporting broader educational impacts, evolving landscapes and global environmental change, and time-variant behavior of faults in magmatic systems and related hazards. And as Andy mentioned, notes and in some cases recordings from those webinars are available on the workshop website, and I would encourage you to check those out. Oops. So to kind of set the stage here a little bit, what are we tasked with? So we, the community, both those of you who are on the webinar today and in general, the community of people who will be attending the workshop, we have a few jobs here. So we've been asked to first identify key science questions that the community will likely be pursuing in 2018 and beyond. And this is, of course, looking towards the recompetition of the existing seismic and geodetic facilities by the National Science Foundation. So first we need to identify key science questions, and then tied to that we need to identify the facilities, seismic, geodetic, and MT facilities that will be needed to support this science. And the organizers of the workshop have asked us to think about 2 different types of facilities. So the first is foundational facilities. So these are the really kind of fundamental capabilities without which we cannot do our science. And then the second type is frontier facilities. So these are new capabilities beyond what exists now, which will be required to make rapid progress in addressing those science questions. So that's really what we're tasked with today, is thinking about these needs. Specifically for this webinar, as Andy mentioned, the webinar will be recorded and archived, and with permission of all the speakers, will be made available on YouTube, along with the past webinars. And then the discussion during the webinar, including your comments and suggestions and input, will be synthesized into a short report. So I will be presenting a 5-minute report on the webinar during the session at the Leesburg meeting devoted to earth structure, rheology, and geodynamics. So the feedback and input that we get during this hour is going to be presented to the workshop attendees and organizers, and will go ultimately into the report from the workshop. So how can you contribute? So please contribute to the discussion during the webinar. As Andy said, the best way to do this is if you can type in comments and questions. I will try to synthesize those for the group and kind of get the discussion going at the end. I hope you'll feel free to follow up with me after the webinar. Please email me if you have additional comments or discussion points that can go into my summary report. And the last thing I'll mention is please submit white papers. So white papers are being solicited in connection with the May workshop and are going to be used ultimately to write the report that's going to go to NSF about future facilities needs. So it is really crucial to get white paper submissions from the community. So please, after you hang up from the webinar, go to your computer and write your white paper. Okay, so just to give you a quick overview of what we're going to be doing during this hour, I have just wrapped up my 5 minutes of overview and introductory material. So I'm now going to turn it over to Jeff Freimuller, who is going to give about a 10-minute talk, basically from the geodesy perspective. And then Paul will give another 10-minute talk from the MT perspective, and then I will talk a little bit from a seismology perspective. So these talks, of course, they're short. They're not meant to be all-encompassing, but they're meant to start the discussion and get discussion going. And then in the last 20 minutes, we'll have open discussion, I hope, from all of the participants. So with that, before I turn it over to Jeff, I do just want to thank you all for typing in your info. So I'm just going to go through so we all sort of know who's in the room here, at least metaphorically. I'm going to go through the list of people who have typed in their names and affiliations. So if you haven't done this yet and would like to, please go to the question box, type in your name, affiliation, and a little bit about what you're interested in. Okay, so just to run through the list, so we have Jean Sauber, who's at NASA Goddard, interested in Earth rheology. We have Anna Calvert, who's at Oregon State, but heading over to the USGS soon. She does magnetotellurics and is interested in water and partial melts in the deep earth. We have Lucy Flesch from Purdue. She's one of the co-organizers of the May workshop, and she's interested in geodynamics. We have Phil Wanamaker on the line. Phil, I don't remember. Yeah, you don't have your affiliation, and I'm blanking. We have Katrin Hafner, who's at the IRIS GSN. Oh, there we go. Here's Phil again, University of Utah. Thank you, Phil. So Phil's an MT person, works on subduction, rifting, and volcanic systems. We have David Simpson, who's formerly at IRIS, former president of IRIS, a seismologist. We have Ronnie Grapenthin, who's at New Mexico Tech and is interested in active tectonics. We have Caroline Began from UCLA, interested in seismic anisotropy and geodynamics. We have Bob Dietrich at IRIS, the current IRIS president. We have a group from the Pascal Instrument Center, so we have Noel Barstow and Panina Miller. We have Luciana Astes, who's currently at NSF in the geophysics program. We have Yuning Fu at JPL Caltech, who's interested in slow slip events and geodetic tectonics. We have Ann Meltzer from Lehigh, who's interested in seismology. We have Corey Reed from the Missouri University of Science and Technology, whose interests are seismology and continental rifting. We have Matt Fouch from K. Young Consulting, interested in seismology and instrumentation. We have John Tabor from IRIS, who's in the E&O group at IRIS. So we have Bill Harbert from the University of Pittsburgh, interested in geophysics and faulting. And we have Levant Izbiliroglu, I apologize if I botched the pronunciation, who is a PhD candidate at Université Joseph Fourier in France and is a seismologist. So that is everybody on my list. I apologize for any mispronunciations of names. And with that, I'd like to turn it over to Jeff Freimuller, who's going to give us a perspective from geodesy. So Jeff, are you on the line here?
Yes, I am. Can you hear me, Maureen?
Yes, I can hear you. Great. So give me just 1 minute to get your slides up here.
Okay, no problem. While you're doing that, I don't have any internet connection where I am, so I'm calling in on my cell phone. I found the quietest place I could, which is behind the hotel near a parking lot. So hopefully it's not too loud. And just let me know when you're ready, Maureen.
Ready when you are, Jeff. Thanks.
Okay, great. So, so you see on the title slide there just a couple of equations, very, very simplified. One is an elastic and one's a viscous constitutive relationship. But what's important here for this purpose is on the right-hand side of each one are strain and strain rate. And so that's what we can measure with geodesy. And so if we know the stresses involved and we know the strains or strain rates that result, then we can determine the rheological properties. If we knew the rheological properties and we know the strains, we could determine the stresses. So this is a powerful tool for looking at structure. Okay, so if you go to the next slide. If you look at the problem of plate kinematics, essentially the kinematic description of plate tectonics works because the forces are balanced. So we think in terms of velocities and constant plate rotations. That's really an indication that forces are balanced. However, even in that case, we can get some rheological insights from kinematic velocity or strain measurements if they're combined with stress. But also, if we look at cases where we have stress changes reveal a lot more about the rheological structure of the Earth. So, for example, earthquakes, and particularly large earthquakes, or changing ice loads are ways of really getting at the Earth's rheological structure that are not easy to do by other means. So if we could go to the next slide. So if we think about the rheological structure, we could look at problems in viscoelasticity. So one example of that is post-seismic deformation. That's not entirely a viscoelastic problem because there's also maybe a fault zone embedded in the material, and the fault zone has its own properties. So we see a combination of the response of the fault zone to a stress change and the response of the Earth itself at a larger scale to the stress change. If we look at changing ice loads, we can look at glacial isostatic adjustment on a variety of timescales. So this can be what's more commonly thought of as GIA from the Last Glacial Maximum when you look at, say, Hudson's Bay or across northern Canada or Scandinavia, but also could be places where the ice loads have changed much more recently, and yet there's already a viscous response because of the structure of the Earth there has a relatively thin lithosphere and low viscosity asthenosphere. So Alaska, parts of Antarctica meet that criterion. We can look at continental tectonics and continental deformation through, for example, a thin sheet approximation, looking at vertically integrated properties of the lithosphere. We can look at elastic structure. We can use earthquakes for that, but of course there's a trade-off with the earthquake source complexity and the elastic structure complexity. Or we can also use tidal loading to probe elastic structure. So I'll briefly introduce these various topics. Next, please. So this slide just shows a couple of examples of observations of post-seismic deformation. On the right-hand side is motion after the Denali Fault earthquake in 2002. And you may not be able to see the numbers on the x-axis, but the horizontal or the divisions on the x-axis are every 10 centimeters. And these are time series of GPS sites, or it's a time series of a GPS site where the pre-earthquake motions have been removed. So this is essentially an estimate of the transient component of the deformation, the post-seismic response. And it's of the magnitude of 20 centimeters or so over the first 5 years after the earthquake. So the key point is that it's a very large signal in response to large earthquakes. On the left-hand side is Uplift that followed the 1964 Alaska earthquake, the second largest earthquake ever recorded, and the post-seismic uplift reached on the order of a meter from that earthquake. So these are very large signals and things that we can fairly easily measure with GPS. The complication is in sorting out the mechanisms and distinguishing between different mechanisms. Next slide, please. So this just shows an example from Parkfield. This is from the Parkfield earthquake, and the sites close to the fault had their post-seismic deformation dominated by afterslip, and in particular shallow afterslip. And the figure on the right shows a time series on a log scale. So the horizontal axis is a log scale, and the vertical axis of displacement is a linear scale. And the key here is that you've got a couple of things. We'll go to the next slide, please. The first is that post-seismic deformation appears to begin immediately after the earthquake. There was no pause of minutes, hours, or even minutes after the earthquake in which post-seismic deformation was not occurring. So if you look at the figure, just take either panel is fine. The horizontal axis, or a horizontal line, is essentially the pre-earthquake trend. And so within the first hour or even 10 minutes after the earthquake, there was already a deviation from that trend. So it indicates that post-seismic deformation began immediately. Also, you can't tell from this figure, but the coseismic and post-seismic mechanisms were different in that they came from different source regions. And you can tell that by comparing the coseismic and post-seismic displacement. So they had to have a different source. And this tells you that all the coseismic estimates include post-seismic deformation. So our key challenge when we look at post-seismic deformation is to separate afterslip, both shallow, like the example here in Parkfield, or deeper afterslip from the overall response of the viscoelastic parts of the Earth. Okay, if we go to the next slide. So now looking at more at the long-term tectonics, this is a figure, a relatively old figure now, from Corné Kramer's global strain rate map, his first version of that from 2003. The hot colors are high strain regions. actually the second invariant of the strain rate tensor that he's plotting here, but high magnitudes, hot colors mean high magnitude strain. So this is entirely derived, or almost entirely derived, from geodetic data. He's also used in places for ternary fault slip rates, but in many places there's nothing but the geodetic data to constrain this. So this is the kind of observation you get of strain rate from dense geodetic measurements. And if you go to the next slide, there have been estimates or attempts to then take, if you take the strain rate and take a model for stresses, you could then infer the effective viscosity of the lithosphere in some sort of a vertically average sense. So this figure comes from one of Lucy Flesch's papers in 2007, and it's a Western North America compilation. So effective viscosity is color-coded. The yellow colors are about 10 to the 21. The red is about 10 to the 20 Pascal seconds. And essentially, this is determined from a combination of modeling the stress field from gravitational potential energy, so internal stresses, as well as basal tractions, and comparing this to the strain field. So you can get estimates about the overall strength of the lithosphere and how that varies, at least laterally, from these sorts of data. And Lucy and Becky Bendick have been working on trying to see how much you can constrain the vertical structure from the data, and that's a more complicated problem. But certainly we can get at lateral variations in the effective rheology by seeing where the strain is concentrated. Okay, the next slide. Okay, next slide is just an example of glacial isostatic adjustment. I'm hearing an echo of myself.
You sound okay to me, Jeff, so I think you can probably keep going. Is that okay?
I'll just go and try to ignore my echo. That's fine. Okay, so this is just an example of glacial isostatic adjustment after last glacial maximum. What you see on the left is data. On the right is the model. The color code is the vertical velocity, which reaches about 1 centimeter per year in Scandinavia. And the horizontal velocities are on the order of 1 millimeter per year or so. And so this is all due to ice that's long gone. We're looking at the viscous response of Earth's mantle to this stress change that occurred thousands of years ago. If we look at the next slide, this is a model result from Alaska, and this is looking at much more recent ice changes. So this comes from Elliott and others, 2010. The red contours are uplift, blue are subsidence. The peak uplift rates are more than 3 centimeters per year, and these uplift rates are driven by the deglaciation that's occurred since the end of the Little Ice Age. So essentially the last 150 years to maybe 200 years at most in parts of southeast Alaska. And because of the low viscosity of the phoenosphere and relatively thin lithosphere, up to, in some places, about 1/3 of this signal, or in some places actually about 2/3 of this signal, are actually a viscous response. And you know, in other places, it's sort of 1 to 2 centimeters per year is actually the response to today's ice loss, and 1 to 2 centimeters per year is the response to the last 200 years of ice loss, not counting the present. So this is again a probe into the elastic and viscoelastic structure of the Earth, as long as you know the ice load history and you can measure the present deformation. And next slide, please. So this has a little animation, which is a tidal model. And this is work by Ito and Simons a few years ago. Normally, we account for ocean loading, the elastic response to the ocean tide.
Hey, Maureen, can you
in
mute
this
your mic?
case,
I'm sorry, Andy?
In this case,
It's your mic is producing the feedback. If you can mute it.
Of course, I'm sorry.
okay. So in this case, Ito and Simons did a kinematic GPS processing where they did not remove any model for the ocean tidal loading. So they're going to use the known loading signal from the ocean tides, in particular one tidal component that's very large off of Cascadia to look at how the solid Earth responds to that load. And so on the right is the observations. Those show essentially the trajectory of motion of the sites in response to the tidal load, and they then inverted that for the elastic structure. So you'll see that in the lower left, they have an estimate of sort of density as a function of depth, and comparing Prem in red with their estimate, which is the blue curve, and the little probability density functions along the blue curve for the variation of density. They also got other elastic parameters estimated out of this as well. So I think that's one more slide. So the last slide here is just a brief talk about future needs. So we definitely need dense long-term measurements of post-seismic transient and GIA or other regions of major load changes to be able to really get at the structure of the Earth. We've so far not been very successful in predicting in advance what the post-seismic deformation from any earthquake would be. And that's because we don't know the viscosity well enough. We may not know the lithospheric thickness well enough. We just don't know these rheological parameters well enough to make good forward predictions until we have some data. So examples are the Denali earthquake in 2002 in Alaska, El Mayor Pucallpa, and future magnitude 7 and greater earthquakes will provide key data for understanding these problems. There's also many other examples worldwide. I just gave some North America examples here. We also need better sampling of GIA across Canada, Alaska, and Antarctica, the places where those signals are very strong. Greenland actually has a very, very dense network right now. If that continues, we've got a great data set from Greenland, but need more from these other places. Then there's also not just looking at the transients, but when we look at the steady velocity field, are there places where this needs to be sampled more densely and more precisely? And that's more of a question for you guys to discuss. But at the large scale, definitely parts of Alaska and the Canadian Cordillera are not sampled very densely. Most of the lower 48 states are, but there are places at the fault system scale where that's not true. And so this is something that we need people to be thinking about. Where are the most outstanding problems at the smaller scales as well as at the large sort of continental scale? And of course, many other examples worldwide. So I've just, again, highlighted North American examples. All right, that's all I've got for my presentation. And I guess we'll turn it over to Paul at this point.
Yeah, thank you, Jeff, very much for that. Especially, I know you're calling in from being on the road, so I appreciate that. And sorry about the microphone feedback issues. I think that was a problem on my end. So yeah, okay. Thanks very much, Jeff. And at this point, I'm going to change the slides. I'm going to turn it over to Paul. And Paul, are you ready to go?
Yes. Can you hear me fine?
All right. Yes, we can. Thanks very much.
I'm going to have to check out Maureen. So.
No problem. Thanks very much, Jeff, especially being on the road.
Okay, no problem. Bye.
Bye-bye. Okay, Paul, take it away.
All right. Thanks, Maureen. All right. Are you muted now, Maureen? Okay. So I guess I'll just start by saying, while this is perhaps my perspective, it does reflect input from a number of other MT researchers, including some who are on the phone right now. So next slide, please. So just to set the stage a little bit, just a brief background, Magnetotellurics is imaging electrical resistivity structure. It's a multi-scale technique which really allows us to image through the entire lithospheric column. In thinking about it in relation to other methods, it's sensitive to minor conducting phases, often at levels below 1%. We are able to capture the 3D complexity of the subsurface and constrain structural anisotropy and, in certain cases, intrinsic anisotropy. And I think an important note, just in thinking about large-scale MT initiatives and facilities, is that MT data are what we call stationary, meaning that you can build up, for example, a national scale data set, in theory, one station at a time without really any loss of fidelity. So it's a little bit different than say, a seismic array where you may need to have a large array out synchronously to capture, say, earthquakes. Next slide, please. So in talking about large-scale MT initiatives and facilities, I think EarthScope, in particular the EarthScope Transportable Array, is kind of the crown jewel. Shown here is the current and funded coverage for the continental U.S., and the red regions are the completed Pacific Northwest and mid-continent footprints. The green regions are what will be completed by the end of EarthScope operations in 2018. And as a side note, you see a few sort of blue areas down in Florida. There's been buy-in from others. This was a recent USGS survey that was completed in Florida. But there remains a large swaths of the continental U.S. And if you actually advance, I think, one slide. Actually, one more even. So everything in white there are areas that will remain untouched by EarthScope. And in addition to this, MT in Alaska is not currently part of the EarthScope operational plan. So while we're talking about big science questions and future facilities, in my opinion, we need to keep in mind that there's really a strong scientific rationale and a future facilities need to support some of the efforts effectively to finish what was started. Next slide, please. So in thinking of the future, I like to look a little bit at the present. There's really been a lot of cutting-edge science that is out there, and it's inherently 3D and based on large arrays such as EarthScope. Shown here are sort of a range of studies. In the upper left is perhaps one of the earliest models of the Pacific Northwest, which revealed a really quite abrupt first-order boundary in the lower crust between hot extending crust beneath the basin range and high lava plains. That's that sort of red area in the uppermost slice, and separating it from sort of cold and unextended crusts to the northwest. There have also been a series of recent papers, two of which are shown on the right, which really, in quite exhaustive detail, looked at the structure and composition and aspects of the tectonic evolution of Western North America, really from the upper crust through to the base of the lithosphere. And in the lower left is, I think, probably the first result from the mid-continent region as regards the magnetotelluric data. And among other things, this paper highlights the progressive assembly of Laurentia and along a series of suture zones and the imprint of the 1.1 GA mid-continent rift system upon it. Next slide, please. So I think just as a very sort of first order look, comparing the Pacific Northwest footprint, which is on the left, to the mid-continent footprint on the right. So here we're looking at resistivity models at comparable lower crustal depths. You can see the stark contrast between the lower crust in these different regions, from the active western U.S. to stable continental interior. And these differences in resistivity to first order reflect variations in temperature, composition, and water content. And the sorts of MT studies that are going on right now are really being used to put quantitative constraints on these variables at various levels throughout the lithospheric column. Next slide. So another area that shows great promise is multiscale wide bandwidth studies embedding high-resolution measurements within a regional background array, such as the EarthScope Transportable Array. And I've just shown kind of two such studies here. On the left is a study actually that Phil Wanamaker led up, looking at a long strike variability in subduction zone fluids as interpreted from a series of focused wideband MT profiles. And these profiles are embedded within the background transportable array, which is sort of the regular grid you see in the background of that upper left image. And there's a lot in this study, but to first order, it's relating these variations in the evolution of subduction fluids to changes in plate coupling, changes in the distribution of seismicity, of episodic tremor and slip, and variations in arc magnetism. Another example on the right is from Yellowstone and the Snake River Plain, and this is actually an example from Anna Kelbert, who is also on the call, where she and others use a pair of high-resolution profiles, which in the lower right are some faint white lines, that were embedded within the Earthscope array. And if you, in the upper right, there's a cross-section, a resistivity cross-section along the Snake River Plain with Yellowstone on the right under the letter Y. And this cross-section was quite interesting in that they interpreted little or no melt in the lower crust and upper mantle beneath Yellowstone proper, but imaged a high conductivity zone consistent with 1 to 3% partial melt in the upper mantle beneath much of the eastern Snake River Plain. Next slide, please. So with that as a bit of background, turning now to the big science questions, subduction zone processes stand out in my mind as low-hanging fruit, in particular looking at fluids from source to sink. So I think there's opportunities to look at fluids in relation to plate coupling, looking at where in the system fluids are being liberated and where they migrate to. Closely tied to this is the porosity structure of the forearc wedge and the overriding plate, and really the hazard implications these present with respect to megathrust events and tsunami generation. I think also looking at the ultimate fate of fluids and the pathways and residence zones for the arc magmas which they generate. Finally, on larger scales, examining fluid transport both into the back arc and much deeper into the mantle transition zone. And as a note, in addressing many of these questions, looking to the future, these really require amphibious experiments with both onshore and offshore components and the instrument facilities to support them. An example is shown in the lower right. This is the MOCA experiment, massive imaging of Cascadia with a huge array. The data collection is complete for this, and this is kind of a quasi-community-driven experiment looking at the fluid budget along the Cascadia margin. Next slide, please. Another big topic is looking at areas of rifting extension, both on land and at sea. And in comparison to convergent margins, I'd argue that our understanding of these environments is more limited. There's questions related to the role of mantle plumes in continental rifting and the development of large igneous provinces. Questions regarding the temperature and water conditions of upper mantle melting, how melt and crustal underplating gets focused within the crust and upper mantle by rheologic heterogeneity. A big topic, which is sort of illustrated on the right, is looking at multiscale interconnections between deep magmatism, geothermal systems, and mineralizing processes. And it looks like I lost my citation. This is actually a paper that Phil Wanamaker put out in 2008. And the upper image is looking at a resistivity section across the eastern Great Basin to Colorado Plateau transition. And they see a very broad conductive region near the base of the crust, which in the lower panel they've interpreted as a region of basaltic underplating, which heat and fluids exhaled from those cooling magmas are feeding hydrothermal systems, which in turn are focused in the upper crust along fault zones. Additionally, I think the interplay, understanding the interplay between faulting, magmatism, volcanism in how rifts initiate and their segmentation is quite interesting. Next slide, please. So I think sort of the final big science question that I'll throw out is really looking in ancient or fossil terrains. And I think there's a lot of opportunity here. For starters, we don't have a good handle on the sources of enhanced lower crustal conductivity in these areas, as opposed to active tectonic regimes where one can interpret these in terms of free aqueous fluids or melt. It's a lot more difficult in areas which have been tectonically quiet for a billion years. There's a lot of opportunity, and I think some of the Earthscope mid-continent work is showing that these studies are able to trace cryptic sort of terrain sutures beneath cover for long distances and really get at the growth of the continent. Looking at processes of tectonic overprinting and modification. Comparison of active to fossil systems where we can on the one hand see these dynamic processes in action and on the other, see their preserved end states. Big questions remain resolving the rheology of the lower lithosphere and the asthenosphere, in particular in relation to the water content and how variable they are. And finally, the processes of craton stabilization, of accretion, and modification of cratonic environments. So I think I only have one more slide. If we could jump one more, thank you. So in thinking about future facilities, I think MT can really play a key role in some of the big future initiatives that are out there, things such as the Subduction Zone Observatory. However, a big need is for a marine MT facility. There's really no current EM analog to OBSIP. What's shown here in the picture is actually what I believe is at least the largest academic marine instrument pool. This is the Scripps Marine EM Lab. And expanding MT, and an important component here, especially when you go offshore, is controlled source EM. Expanding into the offshore environment really requires developing some sort of such a facility, marine facility, or potentially formalizing existing instrument pools into a supported facility. Another area that I think will probably come up again and again is the need for large array studies. And these studies are critical to addressing many of the big picture science questions, but the current instrument pool, at least on the MT side, is limited to less than 100 instruments. And a large fraction of these instruments are sort of taken up for between 6 and 9 months out of the year in support of EarthScope TA operations. So thinking to the future, I think there's some need there. And coupled with this is and this is perhaps a little bit of a side, but a need for uniformity in instrument usage policies. To my knowledge, currently all NSF proposals outside of EarthScope that utilize existing instrumentation need to bear rental costs directly in the proposals. And this model, in my opinion, has both reduced the success rate of proposals and limited the size and scope of a lot of recent experiments. Finally, in order to look at high-resolution, multi-scale studies, there's a real need for wideband instrumentation that I think is currently lacking. This instrumentation is particularly important to looking at the upper crust and is critical, for example, to studies of natural hazards and geothermal resources. So I think I'll leave it there.
All right, thanks a bunch, Paul, for that perspective. And I'm going to, I'm going to go ahead and change over to my slides and give a very quick seismology perspective, and then I do want to leave a little bit of time for discussion, certainly at the end. So this is one seismologist's perspective on important science questions and facilities needs. And as I was preparing this talk, I went back to the 2009 Seismological Grand Challenges document that was edited by Thornley and others, and laid out 10 major grand challenge questions for the seismology community. And by my count, of those 10 grand challenge questions, 5 of them are very closely related to Earth structure, rheology, and geodynamics. And those are the 5 questions that are listed on the slide here. And I won't read them. I'll let you read them. But as I was thinking about sort of big science questions for us to think about in 2018 and beyond, I kind of used the seismology grand challenges as a jumping off point. And I want to just quickly highlight what I think are some interesting recent observations since this 2009 report related to these topics, and how that sort of brings up, new and continuing questions that we'll be asking in 2018 and beyond. Related to the structure and behavior of the lithosphere, these are just a couple of interesting observations that have come out recently. The top figure here is from work by Vedlechik and others looking at lithospheric structure and in particular evidence for shear localization in the lithosphere beneath Southern California. And what they're doing is using S2P receiver functions to look at the base of the lithosphere and seeing evidence for very localized lithospheric thinning beneath rifted regions, suggesting that lithospheric localization or shear localization in the lithosphere really goes all the way to the base of the lithosphere, to the lithosphere-asthenosphere boundary. To my mind, another exciting recent discovery related to lithospheric structure is the discovery of a pervasive mid-lithospheric discontinuity beneath continents. So the bottom left figure shows work by Katie Foster and others. This is an S2P receiver function image of the North American cratonic interior derived mostly from US array data, where they see a reflector that they interpret as the cratonic LAB at a depth of about 230 kilometers, but also this pervasive negative velocity jump at depths internal to the lithosphere, which they interpret as this mid-lithospheric discontinuity. This has been observed in North America and in other continental interiors as well. It really represents a new observation that's quite enigmatic related to lithospheric structure. And then at the bottom right, this is some work from my own group looking at the anisotropic structure of the MLD, and work by Aaron Wirth has shown that we do see a contrast in anisotropy related to this mid-lithospheric discontinuity, at least beneath central North America. The next grand challenge question is the nature of the LAB. So what is the lithosphere-asthenosphere boundary? You know, what is it? Where do we see it? And why do we see it? To highlight a couple of recent observations, the top figures here are figures from work by Tim Stern and others, where they're doing active source imaging of the base of the Pacific Plate as it subducts beneath New Zealand, and seeing evidence for what they interpret as a 10-kilometer thick shear zone at the base of the plate that may correspond to a melt or water-rich channel. Another really interesting recent paper on the nature of the oceanic LAB has come out of Caroline Began's group along with collaborators, and so those are the bottom figures. So Caroline has published a model for azimuthal anisotropy as well as radial anisotropy of the oceanic lithosphere and asthenosphere beneath the Pacific, and then compared that to SS precursor data. And they suggest that the seismic discontinuity, the G discontinuity or the Gutenberg discontinuity, might not actually correspond to the sort of thermally controlled oceanic LAB, and instead they propose a set of processes shown in the cartoon at lower right that might explain some of our enigmatic observations. So a lot of new observations related to the nature of the LAB, and still a lot of unanswered questions to tackle. So when it comes to the evolution of plate boundary systems, I'm really struck, I think, by the insights that we've gotten from the Western U.S., from the U.S. Array Initiative. So, of course, the Western U.S. is an excellent natural laboratory to look at plate boundary evolution, because the plate boundary has undergone significant evolution over the past tens of millions of years. And we have a host of new observations derived from U.S. Array data. So what's shown at upper left, this is a database of SKS splitting measurements, which might be telling us about mantle flow from the work of Kelly Liu and others. At upper right, this is showing attenuation coefficients derived from ambient seismic noise cross correlations from Lawrence and Prieto. And then the bottom images are VP and VS upper mantle tomography models from Schmantz and Humphreys. And I think a really exciting avenue for kind of thinking about this problem is the integration of all these, really detailed, new observations that we're getting from the Western U.S., which really helps us to think about plate boundary evolution processes and then how those processes translate into the structure that we see today. Thinking about patterns of mantle flow and controls on mantle convection, as our ability to do seismic tomography of the mantle sort of continues to mature and get better, we have new models such as the one at upper left from the work of Wei et al. Showing the Pacific slab subducting beneath Asia and showing the slab stagnant in the mantle transition zone. At bottom left, this is work from French et al. This is emphasizing slow anomalies in the mantle, which may correspond to upwellings. And I think, a real robust conclusion that's coming out of these recent tomography models is that all of these structures show behavior that really deviates from the sort of simple end-member convection models, the layered convection versus full mantle convection. We really need to think about the kind of dynamic processes that can explain the structures that we image. Another frontier area that I think is very exciting is looking at seismic anisotropy in the deep mantle. So we kind of routinely use seismic anisotropy to get at flow in the upper mantle. And looking at this in the deep mantle mantle, I think, is a really exciting frontier area for thinking about deep mantle flow. And the top right image is work by Nowacki and co-authors looking at D double prime anisotropy beneath North America. Thinking about internal boundaries and deep Earth dynamics, there's a host of deep, deep mantle structures that have been imaged in more and more detail, and that we need to think about what are the dynamics that are playing into this. So one that I think is particularly interesting is thinking about large low shear velocity provinces, or LLSVPs. So a lot of recent work has taken seismic images of LLSVPs and looked at correlations with expressions of volcanism at the surface. My own group has done some work, along with many other groups, has done work looking at seismic anisotropy that seems to be concentrated at the edges of LLSVPs. So this top right is a figure from work by Colton Linner. And then US Array, as with many of these problems, has really enabled new detailed images of these structures. So the bottom figure is a figure from work by Frost and Ross that used US Array data to look at the edges of the Pacific LLSVP. So there's a very quick tour of some of the science questions that I think are very interesting related to those grand challenge questions. And as I tried to think about what this meant for our facilities needs, one of the unifying themes and needs that really struck me as I thought across these different science problems is the ability to image across multiple scales and with multiple techniques. And Paul mentioned the concept of multiscale imaging in his overview as well. And of course, thinking about multiscale imaging is a very important idea in seismology. This is just a selection of paper titles, and the figure over on the left is a figure from an adjoint tomography model of the upper mantle beneath Europe from the work of Zhu and others, sort of showing structures on a variety of scales. And to me, this is a really kind of important unifying theme for all of these science questions, is we need facilities that will allow us to image across multiple scales and using multiple techniques. And just to think about, one particular example of this, so in order to do multi-scale imaging, of course, we need, theoretical infrastructure and computational infrastructure. We also need infrastructure to collect the kinds of data sets that will really enable this multi-scale imaging. And one example that came to my mind, because this is a project that I'm involved in, this is a map from showing the data collection strategy for the Eastern North American Margin Community Seismic Experiment. This is an ongoing effort to collect a suite of seismic data across the Eastern U.S. passive margin. And a description of all the different data types is shown at the bottom. But I just want to hold this up as one example of a kind of, the kind of data set that we need to sort of think about collecting if we want to do this multi-scale imaging. And this illustrates, kind of a lot of the sorts of facilities and support that the seismology community is going to need going forward to address some of these grand challenge questions. All right, I want to make sure we have at least a few minutes for discussion. I think the speakers, we've all gone a little bit over, but I would like to open it up now for discussion to the group. And as a reminder, these are the kinds of questions that we're thinking about. What are the major science questions related to earth structure, rheology, and geodynamics that's going to drive our science in the near to medium term? What are the foundational facilities that we need to support that science, and what are the frontier facilities? So I know that typing in comments on the GoToWebinar interface is a little awkward for discussion, but please, I'd encourage you now to type in your comments, join the discussion. I'm happy to synthesize comments that people send in, and I'll open it up to the group. And I would encourage you not to all type at once. All right, I'm scrolling through the comments, and I'm mostly seeing stuff related to the echo on the mic, which I think we resolved earlier. Let's see, Luciana had one specific comment on one of the slides that Jeff showed, saying that there have been maybe some critiques of the work of Ito and collaborators that Jeff showed, but the approach is interesting. So there's one kind of specific comment on one of Jeff's slides. but yeah, I would love to hear some discussion. Okay, I have a comment from Matt Fouch, so I'm going to go ahead and read this for the group. So Matt says, thank you to all the presenters for great presentations. One issue not touched upon is the clear necessity for next generation instrumentation. So part of both foundational and frontier facilities. Can you comment on the needs for the seismic and MT communities? So the question for all of us that Matt has posed is really specific to instrumentation. So what are the instruments that, both in terms of foundational and frontier facilities that we're going to need going forward? So please chime in on this. Matt, I'll comment, just one specific thing. So I think the ability to do, kind of Pascal style broadband experiments has been, a crucial part of the seismology facilities that we've had in the past and now and need going forward. One thing that strikes me is that we're starting to do, we are doing science and certainly applying techniques that need, large arrays. So the concept, and this also comes back to the idea of multiscale imaging that I touched on at the end of my talk. We need array data. We need densely sampled, dense sampling of the seismic wave field, and that's enabling new imaging techniques. But in order to do that, we need instrumentation that can be deployed in large numbers. And there have been, recent examples of kind of new ways of doing this. So I'm thinking specifically of the Long Beach array, where this was a recent deployment of, I think, over 5,000 high-frequency instruments, high-frequency sensors in the Long Beach, California area. Very, very dense station sampling and very dense sampling of the seismic wave field. So that's maybe one example. But I see a real need for having, broadband or sort of semi-broadband instruments that can be deployed, easily and in large numbers in a way that's logistically feasible. So, doing, I think there's a science drive. There are science drivers, and there are needs to be able to deploy large numbers of broadband instruments in dense arrays, but the way our current instrumentation, makes it logistically difficult to deploy very large numbers. So looking to instruments that have the capabilities of some of the instruments that we have now, but are easier to deploy in large numbers, to me, that's a need. Does anyone else want to kind of chime in on this? Or Paul, I don't know if you want to kind of comment from the MT side of things.
Is my mic on? Am I good?
Yes, I can hear you.
So from the MT perspective, I would say cheaper magnetic field sensors is a relatively important component that's needed to kind of take MT resources to the next level in terms of large arrays of instruments. Both their cost and the ability to deploy them rapidly. Traditionally, wideband MT, which I think is a critical component of multiscale studies, relies upon induction coil sensors, and a standard MT site requires 3 coils per site, and you're looking at roughly $30,000 for a single site just for the sensors. So I think there's a need to kind of have a lower cost sensor that would allow us to scale up appropriately. Yeah, in my opinion, I think that would be one of the larger needs right now.
Thanks, Paul. Any other comments, either that specifically touch on Matt's point about instrumentation and what our needs are for next generation instrumentation, or more general kind of comments or questions? We are bumping up towards the end of the hour, so it is almost 4 o'clock. So certainly, if we don't have additional comments or discussions, we can wrap up. But we have not had a lot of people chiming in on the question panel, so I want to give everyone one more chance to kind of go ahead and type things in. And I do want to say that if you have not, chimed in on the discussion here via the webinar interface, please do email me comments. I would very much like to get feedback on the points that Jeff and Paul and I made in our short overviews, and I would like to hear from you directly about what we need to pass along to the large group at the meeting next month from the webinar. So please email me, hang up from the webinar, and email me comments or additional questions, feedback, suggestions, because I would very much like to get feedback for the presentation. If there are any other questions, oh, sorry, I'm just scrolling down and seeing that there are quite a few more. Okay, a couple questions I'm going to just synthesize. So Liz Vanacore says that there is a need for ultra deep OBS technology. So the need to be able to deploy OBSs in trenches and subduction zones, so area of the ocean that are very deep. Luciana Astas says one issue to keep in mind is that good quality data and metadata are crucial for good science. I wholeheartedly agree with that point. Data and metadata and infrastructure for archiving and disseminating that data. Caroline Began comments that OBS deployments would help to improve seismic coverage and model resolution. This has been discussed many times. It is obviously expensive, but would represent a big move forward. Miguel Espinoza comments about wanting more data, more GPS data from specifically from Panama, looking at Uplift or Subsidence of the microplate there. And so those are some of the other comments. Okay, I'm not seeing any additional sort of big picture questions, just to respond to the points that several people made about OBS instrumentation. I definitely would second that point and say that, or third that point. I think having the ability to deploy OBSs, in deep water and also in shallow water, it really is expensive but necessary, and is really going to advance the science. I mean, a lot of those fundamental questions we ask related to Earth structure, you have to know what's going on the oceanic plate or on the oceanic side of the plate boundary. All right, I think that we've sort of hit the 4 o'clock hour, so I think that perhaps we should stop there. Thank you all very much for coming. Thanks again to Jeff and Paul for their contributions and for their excellent talks. And again, please send me comments and questions after the webinar, and please go and submit your white papers at the workshop website. So thank you again, and we'll sign off now. Thanks for coming.